is to completely reform the part around a shape. And so, come on. We click there and press that. Excellent. So the two are drawing and stretching, and so in both of these, we're pulling on the edges of the material to make it do something. The difference between these two is a bit theoretical, but anyway, in drawing it keeps its thickness, and in stretching it gets thinner as you stretch it. But anyway, we're taking the material and we're forming it over something. And so it could be a foam block or a form block. They don't have to be super strong because the area across which you're stretching it is really big, so you can make them out of wood and all kinds of things. And you're just grabbing the piece of metal by the edges and pulling it over there, or using a tool to push it onto that shape. So where does this fall on the stress egg? If you're taking this and you grab it on all the edges and form it over the material. Yeah.
It's like the below one part.
The below one? Well, no.
Are you stretching it?
You're just pushing downwards. You
Oh.
just grab it and you push it downwards. It is tension in all directions, and you're deforming it, you're pulling on it, you're deforming it. It's tension in every direction. It's the worst of the bad cases. It is absolutely as bad as you can make it. So you're way out there at 1.4 time because you have tension in every direction. It's awful, but still pretty darn cool. Okay, so remember the little medicine tubes and the Apple Mac Pro where they just squished it with the big die and it squirted up the edges? That was reverse impact extrusion, remember? Well, that's the way that they used to make soda cans, but they stopped making them that way, and the reason is because when you do that, you squash the material, and you're squashing the material in expecting the material that's right under the die to move sideways. I'm applying all the load straight down, and I'm expecting the material to move to the side. And it doesn't really want to do that. And so there's a certain amount of material that just isn't gonna move. No matter how hard I press, it's just gonna stay there. It's not gonna squirt out to the side because I'm pressing down, it doesn't wanna move. So they figured out this process called deep drawing. And so in deep drawing, what we're doing is instead of pressing down with the die, we're grabbing the material and we're pulling it up the sides of the die. So we're drawing the material. And by doing that with the soda cans, they made the bottom, only the bottom, 30% thinner. And by making it 30% thinner, they save about 1/100 of a cent per can. And that's not very much money, but once you start making 1 million cans a day, it starts turning into real cash to save 1/100 of a cent per can. So this is just a really cool process. Unfortunately, it's pretty hard to see in the video, but they will take something that looks like this, and then they will drag it up the sides of the die to make the shape for the can.
The next time you buy a canned soft drink, consider this. That aluminum can will always be recyclable. Unlike plastic, aluminum never deteriorates, no matter how often it's melted down and used again. Aluminum cans are so lightweight that it's hard to believe they're made from a huge roll of aluminum sheeting that weighs almost 10 tons. The sheet is about 5 feet wide and as thin as construction paper. A roll like this is long enough to make 750,000 drink cans. The sheet feeds into a press that punches out round pieces that'll be formed into cans. The punch press actually performs 2 operations. It punches at a disc 5.5 inches in diameter, then bends it into a cup. What's left of the sheet gets compacted and sent back to the aluminum factory, where it's recycled into new rolls. The cup goes into a machine called the draw and iron body maker. A tool draws out the aluminum, forming the body of the can. The tool is lubricated so it won't tear the aluminum while stretching it. The lubricant also acts as a coolant because the aluminum heats up as it's being worked. Once the body is formed, a trimmer cleans and straightens the edge. Now the cans move along upside down on the conveyor belt, over to the washer. The washer performs a 6-stage cleaning. The first 2 washes are in hydrofluoric acid at 140 degrees. The last 4 washes are in deionized water, neutral water with no pH, also at 140 degrees. The cans come out of the washer and go under a hot air dryer. They're now shiny because the hydrofluoric acid wash removed a thin surface layer of aluminum. Next, a roller passes over the cans, coating the bottom rims with varnish. This varnish coating allows the cans to slide easily on the conveyor belts and in the vending machines. It shows up as a blue ring under an ultraviolet light. The cans are now ready to be printed. This rotation printing system can apply up to 5 colors, one at a time. The machine then applies a layer of varnish to protect the ink. This is what the print and varnish process looks like in slow motion. And here's the actual speed, 1,800 cans per minute. Next, the cans fly through an oven that instantly hardens the ink and dries the protective varnish. The next machine sprays a water-based varnish on the inside of the cans. This creates a barrier between the drink and the aluminum, so the drink won't end up tasting like metal. It also prevents the aluminum from being eaten away from the inside by the acid in carbonated drinks. Next, the cans go through a machine called the necker, which forms a 2-inch neck on the can. This is done gradually in 11 steps, so as not to puncture the paper-thin aluminum. The next machine, called the flanger, forms a curved-over edge at the top of the can, which will later attach to the pull tab cover. The cans pass through a sophisticated vision system that photographs the inside of each can. Any can that doesn't meet standards, that has a bump or ink inside, for example, is automatically removed from the production line. They strap the finished cans onto a pallet. From here, they're shipped to the drink company, which fills them and then attaches the pull tab cover.
Okay. The music was stressing you out? So that's pretty cool to be able to form the cans that way, that quickly. Now it looks almost the same, right? They have that big punch sliding forward, but the difference is they're holding the edges of the can, and so as the punch slides forward, they're drawing the material up the outside to make it thinner. There's another pretty cool process that you can do with sheet metal called spinning. So in spinning, what we're doing is we put the piece of sheet metal on a thing that looks like a lathe, and we turn it, and as it is spinning, we shape it around a mandrel. And you can use all kinds of different mandrels. One of the things that they do that's pretty cool, if you have to make something that's going to be closed all the way around such that you couldn't get the mandrel out of the inside, they'll make the mandrel out of ice. And you can form it around the ice and then melt the mandrel out of the middle. So that's kind of a neat thing to do. When you form something by spinning, it puts rotary or circumferential stress into the material and gives it a big strength in the circumferential direction. And that imparts a huge amount of strength to the material. And so if you see things like propane tanks that have the rounded ends of propane tanks are always spun because it gives them stress in exactly the right direction to withstand the loads that it receives by being under pressure. So the ends of a gas bottle, the ends of a big propane tank. Yeah.
When would you want to use like this sort of process versus like doing flat paneling and then injecting it and actually forming it via like hydroforming?
Hydroforming. So this generally, we'll talk about hydroforming in a minute. This can only do something that's axisymmetric.
Yep.
So it can't do something that's a different shape, but this can do something that is much thicker than hydroforming can. So hydroforming is pretty thin material. Sort of car frame is as thick as you can go in hydroforming. Yeah. Okay. So I want you to look for elastic spring back, and yeah, spinning.
To make cookware that's safe for food use, the aluminium must be pure, with no other metals mixed in. It all starts with a round aluminium sheet called a blank, where the pot size and company name are stamped onto what will be the bottom of the pot.
Not quite sure what is so dangerous to be protected from.
The blank is clamped onto a lathe and centered against what's called the chuck, a metal mold shaped like the inside of the desired pot. The lathe spins at 2,000 revolutions per minute, whilst the spinning tool, a round wheel made of a special plastic, is guided by computer as it pushes against the chuck, stretching and shaping the aluminium blank.
Like a rollerblade wheel, but it's big. Big rollerblade.
The machine trims off excess aluminium as it rounds the edges. As aluminium is very expensive, the shavings are sent off to be recycled into other products. After the final trim to size, another lathe moves in to take the sharpness off the edge. It's taken 4 minutes to spin this 32-litre pot. Handle holes are then punched out. Then aluminium handles are riveted on. This part is now finished. Items that aren't as large and heavy are spun on the lathe. An experienced metal spinner is needed because this trade isn't mechanical science. You've got to have a feel for it. Besides cookware, many other aluminium products are spun on a lathe. This is a light reflector, a round aluminium fixture that surrounds light bulbs in factories, shops and stadiums. When working the hand lathe, the metal spinner uses what's called a scissor tool. It's the equivalent of the plastic wheel on the automated lathe. As the blank spins, he moves the tool further and further down to stretch the aluminium into the right shape. This is a sausage funnel. This will be the inside tube of a cake tin. The metalworker makes the body of the cake tin on a different lathe.
All right. So anyway, you can see that in all of your aluminum pots like that. If you have stock pots, if you look at them, you will see a circumferential shape to the structure, and that is because it was formed by a spinning process. So there is strength that it gains by doing that. Also the ability to form that flat thing into something that has a huge amount of deformation. So when we think about this, this is all cold work, and yet the amount of deformation is way past the 10 to 30% that we would normally expect to be able to do. But you can do that because you continue to form it in little bits, continue to form, and you make it. Now, there is, of course, another way.
Using a variety of tools to get a variety of effects. This can be spun. The chef.
Okay, now we're going to get to the next one. YouTube, I have no idea what you're doing. Okay. You can hydroform. So in hydroforming, instead of taking that thing and using a stick to form it, in hydroforming you use high pressure water or high pressure oil to push the part into a mold. This does not have to be axisymmetric. It can be all kinds of different shapes. So if you have an aluminum bike, most likely the tubes on the aluminum bike, if they're non-circular, they were made by hydroforming. So you make a mold, you blow them up essentially into the mold. We did this when I was an undergrad as a way to make giant tanks. So when you have big spherical tanks, they make them out of things that look like orange peels. Those are very expensive to make and very expensive to transport, and they limit the size that you can make the tank. And so this one professor that I was working with a little bit had this idea of if you made them out of pieces like a soccer ball and you welded the edges together for the soccer ball and then just inflated it with water, you could make it circular. And it turns out the answer was yes, you could, and no, it was not less expensive. So it was an interesting idea. But anyway, you take it, you have a die, you plug both ends of the tube, and you pressurize it, and it will form into that shape. Almost every suspension member of your car or frame member of your car was hydroformed, especially if you have a body-on-frame vehicle, then all of that was hydroformed, but even in others, it was. So it's a very fast process. You hook it up, it goes, it takes a couple of seconds, and it forms. But it's not the fastest process. Say, instead, let's see if we can skip the video, because we don't really want to know about Jones hydroforming today. So let's say that you needed to do something bigger than hydroforming. And you needed, a huge part, and you needed to shape the part quickly. Remember we talked about superplasticity, where if I form something fast enough, it actually internal to the material heats it, and it will form and shape out of the way, and I can get way more than the 10 to 30% deformation that I wanted in a single step. And so you might be thinking to yourself, well, that's cool, but how do I get that much energy? And the answer is, you get yourself a tank of water, and you put a big explosive charge in the top of it, and then you stretch the piece of metal across the shape that you want it to be. You draw a vacuum on the backside if you want to, just to help it out. And then you set that off, and the pressure wave will form it into that shape, all in a matter of a part of a second. And so that's just pretty darn cool. This is called high energy rate forming, and it's how they make the cockpit on an A380 when they made A380s back before they stopped making A380s. So that's a massive piece of metal formed into that shape in one single go. So let's say that, you know, by some unfortunate experience, the ATF has your name and number and they don't sell you explosive charges anymore, so you need to do it some other way. Well, it turns out it's still okay, because you can do it with a really big capacitor bank and 2 electrodes and just short the 2 electrodes together, and it will form an explosion, an explosive pressure wave that will form the material into the same shape. So it's okay, even if you're on one of those lists. You can still do this. Yeah?
How thick is that metal?
Sorry?
How thick is that?
Not super thick, no.
Okay.
It's relatively thin, I would say 1/4 inch or less usually.
Okay.
Yeah.
I was gonna say that's a lot of water to not get out of the way for.
It is, but the water does, the water transmit pressure waves so well to the material, it really does a good job of helping that out.
If it explodes, can you reuse the electrodes?
I don't think so. I think they're done. Yeah, I think you make new electrodes each time, but if you make them out of something like graphite, then they're relatively inexpensive. Yeah?
Do you know how much energy goes into the electrical version of this? A lot?
Yeah.
Okay.
No, I don't. Something equivalent to the explosive in the last one, so a big number. I got to work on a project when I was in high school where we were, my job was to design a rack to hold these capacitors. And the capacitors were about 2.5 feet tall, 8 inches wide, 24 inches long, and we had 24 of them. And to run this accelerator, so the point was it was going to blast stuff out of space with a neutral particle beam. And so to test this, you had to have this huge power surge. And so the way that they would do it was they would charge these capacitors up for about a day, and then they had this huge copper bar, and they would drop the bar so that it would short out all the capacitors at just the same moment, and then from the capacitor there were huge cables that went off to a big system that would make a neutral particle beam happen. And so I got to design the rack that held those big capacitors, and it was pretty cool, but it was not this much power, I think, because nothing exploded in this if you did it right. However, when you wanted to go work in this room, it was kind of funny. You would open the door to the room, and then there were these hooks right there. And so you'd take these hooks, and they had big grounding cables on them, and you'd sort of fish around in the room and make sure no lightning hit the hook. And then you would reach it in there, and you would hook it on something. And there were these 3 places that you had to hook it to make sure that the whole system was grounded before you went in. And anytime you were in the room, you never pointed at anything. You would always talk about it, and you could kind of nod your head towards it, but you never pointed at it, because if anything happened to have any stray voltage left on it and you pointed at it, you would become the path to ground. And so it was kind of an interesting room, but you know, it's good for high schoolers to work on things like that. All right. Thursday, world famous manufacturing challenge.
What does this mean?
It's awesome. It's gonna be good.
It's awesome.
It's okay.
I'm really excited.
And class evaluations and the test. You'll receive the test. If for some reason you missed Thursday, the test will also be on Canvas, but you should not miss Thursday, because then you miss the world famous manufacturing challenge.
We don't want that.
And you do not want that. All right.
Are we done?